So this is our report for the absorbance lab. Our goal for this experiment was to calculate and compare the absorbance and fluorescence of the dye fluorescein using spectroscopy. We then had to relate Beer's law to our findings and explain how useful spectroscopy can be for scientists.
We hypothesized that the greater amount of light absorbed would correlate to the lesser amount of fluorescence we would observe.
Then we created absorbance and fluorescence spectra of fluorescein. And we found that our fluorescence spectra was much greater than our absorbance spectra due to the fact that the dye can only absorb certain wavelengths of light.
The most intense from the fluorescence is also the wavelength where the regular is absorbed the most.
In order to test our hypothesis, a spectrometer was set up where we taped a spectrometer light measure and a flashlight down to the table to ensure that a stable reading was taken. This can be seen in the top left corner. Then we measured the intensity of plain water in a cuvette to get the I naught value in Beer's law equation. Then we measured the intensity of the purple dye to get the I in Beer's law. From there, the data was exported into Excel and we created an absorbance graph using Beer's law. From there, we determined what dye we have. And then we took the light measured from fluorescein, and that setup was different because we had to set up the flashlight at a 90-degree angle in order to only get the light that was emitted from the fluorescein and not from the flashlight. This can be seen in the top right corner. From there, we exported the data into Excel and created a fluorescence spectra. Throughout the experiment, we assumed that no other light from the room was affecting our data and that the only light we measured from the fluorescein was the fluorescent light.
An absorbance spectra, then, is a graph that shows how well the substance can absorb light over varying wavelengths. Some uses of absorption spectra are identification of unknown substances, detecting impurities of organic substances, and solving for concentration of substances. Fluorescence, on the other hand, is the light emitted from a substance due to the substance's inability to absorb that wavelength. A fluorescence spectra, then, is a graph that shows how much light or photons of light is emitted from a substance over varying wavelengths. Some uses of fluorescence spectra include identification of proteins and detection of biological compounds present in low concentration.
For our models, we are using Beer's law, which measures peak absorbance, and it uses the logarithmic ratio of intensities. The E means extinction coefficient, the L is for path length, and C is for concentration. Those variables are only involved when solving for the concentration of the dye, and the extinction coefficient comes from graphs that were already made available to us. Our other model is figure 1.2, and it represents how electrons are excited and emitted in a fluorescent substance. Initially, a higher energy photon will come in and excite electrons, and eventually the electrons will go to a ground level state and release a photon of lower energy.
Using our setup in the spectrometer, we were able to get the intensity values for different substances. On the right, you can see the two graphs for the intensity of water, which is used as a control, and the intensity of the fluorescein, which is what we're using for this experiment. Using these values, we could determine the absorbance of the fluorescein by using the log of the initial intensity, which would be the water, and then the intensity I is fluorescein. Example calculation is given at 450 nanometers, doing the log of one over the other to yield 0.324. This is shown on the next slide, which you can see there on the left axis is the absorbance, which is that calculated value, and that is going directly through the substance. And you can see that in blue. And then on the right axis, you can see the fluorescence intensity, which is also graphed, and that is just using the direct values that were given at the spectrometer when we were at the different setup measuring it from the side. As you can see, different wavelengths are being absorbed and different wavelengths are being intensified and released, emitted. So the reason that a certain wavelength proton goes in and a different wavelength comes out is because some of it is being absorbed. If a different wavelength comes out then goes in, energy is still conserved because the material is absorbing that, and just because it's not re-emitting it out into the environment doesn't mean that that energy is lost.
So for our findings, we initially utilized the intensity data found for the water cuvette and the unknown dye cuvette to calculate for the absorption spectrum. Important note is that most intense from fluorescein is also the wavelength where the regular is absorbed the most. So in conclusion, spectroscopy is a very useful tool for scientists to find unknown samples, as you are able to measure intensity and then get absorbance and fluorescence of unknown samples. Beer's law plays a great part to find absorbance values, to find and solve for concentration of solutions. And due to limitations of wavelengths that the dye can absorb, the rest of the energy from the photons of light that are emitted are seen as fluorescein, which is why our fluorescein spectra was so much greater than our absorption spectra. And finally, some possible errors and limitations in our lab was that outside light sources may have influenced our data collection, and the position of the spectrophotometer may not have been positioned at the highest intensity.